introduce today's speaker, Dr. Chetankumar Jalihal. He works as an assistant professor in the Department of Climate Change at the Indian Institute of Technology, Hyderabad, where he leads the Climate Evolution and Dynamics Research Group. His research focuses on developing new theoretical frameworks to advance our understanding of monsoon dynamics, while also investigating Earth's ancient climate and its evolution. His work bridges the fundamental climate theory with paleoclimate science, providing valuable insights into the processes that shape the climate system. He's also an Inspire Faculty Fellow and was a Humboldt Postdoctoral Fellow at Max Planck Institute of Meteorology in Hamburg, Germany. He's completed both his master's and PhD at IISc Bangalore, where he was recognized with his Best PhD Thesis Award. He subsequently carried out his postdoctoral research at Max Planck, further strengthening his expertise in climate dynamics. On that note, we are delighted to have Dr. Jalihal today with us, and I would like to welcome you.
Hello. Very good afternoon, everyone. Thank you very much, Director Suraj, for having me here. So, most of this work was done at Max Planck Institute, and also some part of it I did last year at IIT Hyderabad. So that's my PhD postdoc supervisor, Uwe Mikolayevich. So together we had been looking into some interesting simulations, and one thing led to the other, and this is what we came up with. So before I begin, I want to briefly give a broad overview about my own research. This is the way I think of my research. Suppose you go to a lake, and there is the signboard which says average depth is 4 feet. For most of us, this is not of much concern. You would get into the water, right? But suppose instead the signboard says this, that it is 20 feet at places. Then if you do not know swimming, you won't get into this water, right? So this is a very simple message from this, and this is how I think of my work. So the message is that if you can handle the worst case scenario, you can handle everything else, right? So how is this connected with monsoons? So monsoon theories are based on modern observations. That is last 30-40 years of very good data, global coverage, and maybe a couple of decades more of reanalysis data. So most of the theories are based on this 30-40 years of good data, which is like this 4 feet of water. The real test of monsoon theories is somewhere in the trenches. So that is based on the modern observations, what do we know? Some of the theories like Landsea temperature contrast theory, which has been kind of discredited in the last couple of decades. People have moved on to the meridional shifts in ITCZ, which is based on energy conservation between the two hemispheres. So this is now the more accepted hypothesis or theory of monsoon. Now, the real test of these theories is in the deeper waters. So for me, these deeper waters are paleoclimates. Why? Because in paleoclimates, Earth's orbit is very different. Greenhouse gases are naturally different, and ice sheet configurations are different. So you're in a very different climate state. So if the same theory, which works in modern observations, also holds true in very different climate states, then that's a good theory. If not, then our assumptions are needs some correction. Its course correction is required. So this is a broad overview of my work. So this is what I do: use modern theories in very different climate states and understand what's happening. So this is where most of my work is. I use large, very long transient simulations spanning over multiple thousands of years, tens of thousands of years, and I am also able to understand differences between or quantify forcing and feedback on monsoon systems. So that's one of the aspects that comes out of this. More recently, I have been doing something quite interesting. So this is somewhere at the bottom of this trench. So that is why we have some very interesting fictitious thought experiments. So one such experiment is the retrograde Earth experiment. You reverse the Earth's rotation. So most of the things remain the same. All boundary conditions are same. Only the sense of the direction of rotation is being changed. With only this one thing changing, we happen to get a monsoon over Sahara. So conventional theories suggest that we should have mountains to the north or albedo should be low. So this is a special case where it offers some opportunity to understand what really is happening and maybe correct or course correct some of the assumptions in our monsoon theories. So today, most of what I will be discussing is related to this experiment. So monsoons and deserts. So this is one of the reasons why I want to compare monsoons and deserts, because mainly in this experiment, a desert becomes monsoon. So that's why monsoon and desert. So before I begin, a little bit of what's actually happening in the modern world. Right, before we get into a fictitious world, let's look at what's happening in the real world. This is a map which I took 1 month ago. This is ERA 5 forecast. At around, this is at 1 p.m. It is 10th of June. Okay, monsoon onset had just begun and then monsoon had disappeared. Right. So if you look at the surface temperatures, you will see that most of North India is as hot as Middle East or Sahara, right? So this is not a one-off event. This happens every year. In fact, this is what happens in climatology. This is observation, okay? Land temperature. As the seasons progress in May, June, North India is at the same temperatures as Sahara, Middle East. So India behaves like a desert during non-monsoon months. Come monsoon, it's a very different game, right? So there is, in some sense, a desert to monsoon transition that occurs, and that's what also excites me. It is along the same line as the desert to monsoon transition in the reverse rotating world. So if we look at the general rule that we have come across in textbooks, we have these Hadley cells, right? Ascent at equator, subsidence in the subtropics on either side. Right? So that's the general rule. So subtropical deserts is a general rule, but there is an exception to this rule. That is the South Asian monsoon, which is at almost the same latitudes as Sahara, Middle East, but it does not follow the same subtropical descent that we see over Sahara, Middle East. So if subtropical desert is the general rule, monsoon is an exception to this rule. Right? What I'm interested in is the transition, in this transition that occurs. Not the fully developed monsoon, but the transition of this monsoon. Right? So also, if you notice at these latitudes, longitudes, the zonal asymmetries are the strongest. The zonal asymmetries are the strongest. So before we delve into this, a very brief overview of the different theories of deserts. A lot of work is done here on monsoon, so I won't go into that. I will directly discuss about deserts and then make a comparison between the two. The first theory is the descending branch of Hadley cell. So this is something we already saw a couple of slides ago. So this is during March, April, May, climatology, stream function. So you have ascent here, descent on either sides, right? But what really happens during June, July, August, the summertime, is that this is the, what you see here, that's the winter cell. Winter cell is in the northern hemisphere. It's very strong. So ascent is somewhere around 10 to 15 north. And the summer cell is very weak. So this is in the zonal mean. Summer cell itself is very weak. So there is no strong descent that you would that is associated with descent over Sahara, which will come out of this theory. So it is only in the annual mean or during the transition months, March, April, May, or September, October, November. But during June, July, August, you don't see a strong descent over here, which is necessary for Sahara to be a desert. So the next hypothesis comes from albedo and radiative cooling, going back to Charney, 1975. So if we look at the top of atmosphere radiative fluxes, this is F2 net fluxes at the top of atmosphere. This is from series satellite observation, climatology, and this is ERA 5. They are very similar. So during June, July, August, the South Asian region is very positive. There is net heating of the atmosphere. Right? Over Middle East, Sahara, there are negative regions. So there is radiative cooling, net radiative cooling. And net radiative cooling is associated with descent. Right? So this is very clearly seen in observation and reanalysis. So Charney in 1975 suggested that it is this subsidence or descent associated with the radiative cooling which creates the subsidence over this region. And why is radiative cooling very strong over here? It is because of high albedo. Sahara and Middle East, they have very bright sand, no vegetation. So a lot of shortwave is reflected back to space, right? And that creates radiative cooling subsidence and subsidence. Now, this explains why subsidence occurs during June, July, August, which the Hadley cell theory did not explain. So this is an improvement over that initial theory. But to be absolutely precise, Charney did not make this proposition. His main proposition was the albedo vegetation feedback. So mainly he was talking about region somewhere here, Sahel, the desert monsoon transition zone, where what he said was due to overgrazing, land becomes barren. It is more reflective compared to when it was vegetated. That leads to high albedo, subsidence, arid climate, because you are suppressing convection. And then this is the feedback loop that exists. Right? So this was the proposition that Charney made. But subsequently, many others have proven that this is not a major or dominant feedback mechanism that is prevalent in these regions. It is related with SST. So there are decadal oscillations in the Atlantic Ocean, in Pacific Ocean, which trigger these type of events rather than albedo. So that was about radiative cooling and subsidence. But still, many theories consider high albedo as a necessary condition for subsidence to exist. Okay. Now the next theory is Rodwell-Hoskins mechanism. So this is where things are quite interesting. What Rodwell-Hoskins proposed is that during monsoon season we have very strong diabatic heating over the South Asian region. Now that triggers a subsidence over here through Rossby waves. So it is not a direct Hadley-like cell. So from ascent over here in South Asia and descent over here in over Sahara, that is not how it works. The Hadley cell here the ascent here creates very strong diabatic heating, which leads to changes in isentropic surfaces and descent over here in the desert. So it's a different mechanism. The air mass descending over here is coming from mid-latitude. It's coming from here, from the mid-latitude. So this has been a very strong theory, but it appeals to dynamics, right? Atmospheric dynamics. There is diabatic heating. In this place, and then subsidence over here. This is very nicely covered in Suraj et al. 2021. Very good introduction to all the desert mechanisms. But there are a couple of drawbacks of this theory. It assumes a monsoon heating. What creates monsoon heating, they are not discussing. So given monsoon heating, you should have subsidence to the west side of the monsoon. This is the proposition. And it assumes that deserts are a passive response to monsoon. In reality, there is some feedback coming from deserts as well. So it's a two-way mechanism, but this theory focuses more on one side only. So now coming to a slightly different perspective, energetics of monsoons and deserts. Why this? Because over the last couple of decades, we have moved from land-sea temperature contrast theory of monsoon to energetics of monsoon. What is energetics of monsoon? It is conservation of energy, same theory as for ITCZ, but over monsoon regions. So here you look for conservation in 2D. In ITCZ, energy is transported from one hemisphere to the other hemisphere. Here, energy is transported in both directions, north, south, and east, west. So you're just extending energetics of ITCZ to monsoon region. So this has been a emerging framework of monsoons. Now, here we will say that energetics of monsoons can also be extended to deserts. And we will use this to understand what happens at the time of monsoon transition in modern climate and also in the reverse rotating world. So what is this energetics? Here is a very brief introduction. So this is from derivations from Nilin and Head 1987. This is the equation that they proposed. Let me explain this equation. On the left-hand side, we have a low-level mass convergence. So this 2 here is referring to the lower troposphere. And in the numerator, you have F2 minus surface energy fluxes. So this is the total energy going into the atmosphere. So basically energy from the top and energy from the surface, right? So both of these going into this monsoon domain. And this guy here, that is the mass convergence in the lower troposphere. And this will be exactly equal to the mass divergence in the upper troposphere. Now, this is divided by GMS, gross moist stability. Now, gross moist stability is a term that somewhat relates to the thermodynamic stability of the atmosphere, but more accurately, it represents the efficiency of the monsoon system in exporting this energy. Okay. So there are two assumptions here, that it's a steady state condition and it's a two-layer atmosphere. Okay. So now we will do this only for land. So surface energy fluxes over land can be, total surface energy fluxes can be considered negligible because land has lower thermal heat capacity. So we will get only an equation which connects top of atmosphere radiative fluxes to the low level mass convergence. Okay. So now this is a very interesting, very comprehensive equation because the numerator here is radiation, radiative fluxes, denominator represents thermodynamics of atmosphere, and this guy over here, that's dynamics. So this is one equation that combines the three different aspects of atmospheric sciences or atmospheric physics. There is dynamics, radiative heat transfer, and thermodynamics, all of them coming together. So this is a very interesting equation for monsoon. Now, there is one other version of this equation that is used in literature, derived by Srinivasan in 2001. What we do is multiply the both sides by water vapor. So basically, you are converging moisture in this region now, which is P minus E, moisture convergence. And on this side, you will have F2 divided by GMS by water vapor. So this is a different version of GMS. Okay, it still represents the same quantity. Now, just that instead of mass convergence, we have P minus E. In this talk, I will use these two interchangeably. Essentially, they are the same. Okay. Now, how does this theory for mass convergence, how can this theory be used for deserts where you have mass divergence? So now I will go one slide back. This was for monsoon region. You have convection here, mass convergence in the lower troposphere, mass divergence in the upper troposphere. Now, over a desert region, you have upper level convergence, right, and low level subsidence here, no clouds, and divergence in the lower troposphere. And this has to be balanced by top of atmosphere radiative fluxes at all times. Comes from energy conservation, simple energy conservation. So this equation ideally should also be applicable for deserts, but surprisingly, this was not done in literature until now. So in this case, what does GMS represent? It would be the, so what is happening here is that energy is being imported into this desert regions to balance the loss of energy at the top of atmosphere. Okay, so GMS in this case represents the efficiency of import of MSC, moist static energy, into this domain. Okay, so the same equation can be used for deserts. So here is one, from ERA 5. This is the same picture which I showed earlier. You have negative radiative fluxes over here over Sahara, right? We saw that this is because of albedo, high albedo, more reflectivity, radiative cooling. F2 is negative, F2 is positive over here. Now, if we look at that equation, if F2 is positive, GMS is positive, then you have low level mass convergence. So that is what is happening over South Asia. Now, over the desert region, F2 is negative, and GMS is positive. So you get a negative term over here. So that translates to low level mass divergence. Okay, that is what's happening here. So now what we will do is we will take these two regions, these two boxes, and look at what causes these differences in top of atmosphere radiative fluxes. It has already been discussed in literature that it is related to albedo, but we will relook at it, revisit that. So here is a decomposition of F2, the difference between these two regions. So it is positive because I'm doing South Asia minus Sahara. Now it is split into two components, the reflected shortwave and OLR. Surface fluxes are 0 because I'm considering only land credits. So if you look at this, surprisingly, albedo contribution is smaller compared to OLR. So this was a very interesting insight. Until now, F2R negative over this region was attributed to albedo, but the contributions from aridity, because it's dry, all of the long wave efficiently radiates to space. The contribution of that aspect was not quantified. So here we see that OLR is very important. In fact, this guy is negative. Reflectivity is negative, which means South Asia is reflecting more short wave than Sahara is. Why? Because it's cloud covered. Clouds are way more reflective than sand. So in terms of albedo, South Asia is more reflective. So it is OLR that determines the F2R negative over Sahara, not albedo. I mean, albedo is important, but not the biggest term. So OLR consists of two parts, right? There is clear sky, cloudy sky. So we can split this further. We have done some nuanced calculation here. There is consideration about cloud area fraction, things like that. But essentially, we have clear sky, and all of these put together, that's cloudy sky. So we have clear sky and cloudy sky almost close to each other. I mean, they are having equal contribution to the OLR. So cloudy sky, we can understand, cloud covered, so emission from very high altitude. So that's why its contribution is there. But what about clear sky? Why is clear sky so dominant? So that is what we will examine in the subsequent slides. But before we get into it, here is the seasonal cycle of F2R in gray. So that's the plot on the left side. For South Asia and Sahara, those two boxes which I showed earlier. So Sahara is in dotted line, South Asia is in the solid line. If you look at it carefully, during the non-monsoon months, it is negative in both the regions. F2R is negative in both the regions. You have subsidence and F2R is negative. During monsoon season, South Asia is very strong and positive, and even before monsoon season, it has already become positive. Sahara becomes slightly positive because this is averaged over the whole box. If you look at this region here, there are many negative F2R negative regions, but averaged over this entire box, it's coming out to be small positive during some of the months. So that is one thing. Now, if we look at the individual contribution, absorbed shortwave and OLR, you will see that absorbed shortwave is pretty much similar during all the months except the monsoon months. During monsoon months, there is a sudden change in South Asia, and that is cloud related. But the biggest changes are in the OLR. So once again, confirming the result in the previous slide. Just that the difference here is we are using seasonal cycle. You can see that even before monsoon, March, April, May, already there is divergence in OLR between the two regions. This is the strongest contribution and not albedo. So now what I will do is I will directly give you the main result and then give evidence for that main result through reanalysis datasets itself. So the main result is that we figured out there are certain feedbacks that are occurring during monsoon onset, because of which OLR is very different. So this part is understandable. It is coming through clouds, but pre-monsoon, when there is not much cloud cover, what is happening? So that is what we will look into now. Okay.
Chetan?
Yeah.
So, show your previous books. How do you treat the ocean part? Like, as part of their book and all.
Yeah. So in this particular calculation, I have ignored. I have taken only land grids. But even if I take ocean grids here, it turns out that northern Bay of Bengal net surface energy fluxes is negligible. It is almost same as land. So whether I include it or not, it will not affect these results. No, during monsoon. Pre-monsoon, maybe the results may be different. My considerations here are using only land. Yes. No, that is on those time scales. On those time scales, there are some surface fluxes which will contribute, but this is only between desert and monsoon. What is the main difference? It is at the top of atmosphere and not surface. So now going to the main mechanism, So what is happening is that just before monsoon onset, few pentards before monsoon onset, there is this equation is being influenced. So OLR will decrease. In other words, the numerator is increasing. If numerator increases, then this will have to balance it. So there will be a feedback from numerator into the large scale forcing, right? And this will increase. If that increases, then there will be more moisture advection into this region. More moisture advection, more impact on OLR, clear sky OLR, right? That will decrease, numerator will increase, which has to be balanced by large scale circulation. So this will increase even further, right? So this will go on for some time. The moment onset occurs, you have clouds, right? Clouds will have a very different effect. Clouds will strongly impact OLR even further, and also albedo. Both of these are getting affected. So now it is a different game. Now the numerator is going to be influenced by water vapor, clouds, cloud contribution to OLR, cloud contribution to albedo. Okay. So now this is where the mechanism here was related to what happens pre-monsoon. So this is the mechanism that that we were able to tease out using the reverse rotating world and also by comparing monsoon and Sahara. Now I will give the proof for this mechanism. So here is from era 5. I'm considering only OLR. Okay, why OLR? Because we saw OLR is the biggest difference between Sahara and South Asia. So I'm going to take only OLR. This is difference in OLR between South Asia and Sahara in black. That is the OLR. Okay. I have used offline RRTMG radiator transfer model with era 5 profiles to calculate contribution of cloud, water vapor, and surface temperature. These are the three most important parameters that contribute to OLR at the top of atmosphere. So, interestingly, surface temperature does not contribute that much during the time of onset. So, let me back up a little bit, explain the x-axis. So, this has been aligned to the local onset date. So this is over many grids over here. For each grid, I calculate the onset date, align everything to the onset date of that grid. And then this is the average. What is plotted here is the average of all the grids after aligning them to the onset date. Okay. Now, in blue is water vapor, in gray is clouds. This is the onset date. Just before the onset date, you have large contribution of clouds. And clouds continue to contribute to difference in OLR throughout. Now, water vapor is important a few days before onset. Blue is closer to black up till some point, and then pre-monsoon showers occur and clouds begin to take over. So you can see that the impact of water vapor is present few weeks or few pentards before onset, and subsequently clouds will take over. So this is one proof of the mechanism that I showed earlier. So here is another way to look at it. Here is again for the same two regions from era 5. What is plotted is a scatter of pentard climatology. X-axis is water vapor here. Y-axis is clear sky OLR. Okay, I'm considering only clear sky OLR. On this side, it is clear sky OLR and surface temperature, the two important factors for clear sky OLR. Right? The plus is Sahara, circle is South Asia. If you look at Sahara, the different colors are different months. Okay, Sahara is very linear with surface temperature. It is clear sky all throughout and no much water vapor, not much water vapor. So it is very linear with surface temperature. But the connection with water vapor is not so strong or not linear. There is some very non-linear influence, but it's not so much as surface temperature. South Asia, things are very interesting. During the non-monsoon months, it is linear with surface temperature. Come monsoon, this linearity breaks down. And during those months, April, May, June, July, August, September, October, so you have to look for pink, red, orange, two shades of orange and purple. So these are the colors which you can see influence of water vapor is much higher. So in fact, influence of water vapor becomes more important after it crosses somewhere a threshold of 25 kgs per meter square. Sahara never crosses that threshold. So it remains in the regime where clear sky OLR is determined by surface temperature. But South Asian monsoon, because of large scale forcing, is able to pump enough water into this region that clear sky OLR is influenced, that feeds back into large scale circulation, and you have a feedback between radiative heating and large scale dynamics. So that enables abrupt onset over this region. So this is one way to look at it. Another way is through radiative transfer model. This is Sahara. This is clear sky OLR in black, and contribution from water vapor in blue, and temperature in red. So you can see that black and red are together throughout the year. So influence of temperature, surface temperature on OLR, clear sky OLR, is very evident in Sahara. But in South Asia, the black and red are together during non-monsoon months. During monsoon months, it's water vapor that's controlling the clear sky OLR. So the influence of water vapor is once again shown in a different way. So I will summarize this part. Monsoons and deserts can be thought of as radiation circulation paradigm. They are basically a balance between radiative heating or cooling at the top of atmosphere and low-level mass convergence or mass divergence. So these two opposing or contrasting climates can be considered as radiation circulation systems in opposite directions. Earlier, there was a lot of discussion about albedo feedback on monsoon, or albedo as a limiting factor of monsoon. We show that water vapor radiative effects are very important. That helps in the growth of monsoon over the South Asian region. So it's an internal feedback to the monsoon system. So monsoon has been thought of as something where external forcings drive it, be it the interhemispheric temperature contrast or the land sea temperature contrast, but feedbacks internal to the monsoon system were not given enough attention. And here is one example where we can show that internal feedbacks also are playing a role. Now, suppose a hypothetical question, given this summary, if we are able to pump enough moisture over Sahara, then can we trigger monsoon? Why this question? Because previous theories suggest that albedo is a limiting factor of monsoon. So what about moisture? What about this effect that we saw, moisture impact on OLR? Can we still trigger monsoon? So that is where the reverse rotating experiment comes into picture. This is just a extreme case scenario to tease out or to showcase the same mechanism. Now this is from a climate model simulation, MPI ESM. This is the control, retro, June, July, August climatological precipitation. So you have the South Asian monsoon. It's a very coarse model, 3.75 degrees, because it's integrated for 8,000 years. So we had to compromise with the resolution of the model. You have this Wampool convection over here, South Asian monsoon, Sahel, arid regions over here. As good or as bad as any other CMIP 6 or CMIP 5 models. Okay? So typical climatology that we get in any model or in modern observation. Now in retro, when you spin the Earth in the opposite direction, you get very strong monsoon over Arabian Sea, Middle East, Sahara, these regions which are arid over here. Now the arid climate shifts into East Asia, Northwest Pacific. So there is a reversal of this of this zonal asymmetry, which we see over here. The zonal asymmetry is now reversed. So we will now use the energetics of monsoons and deserts to understand what causes Sahara to go from this into this, transition from one state to another state. So I'll tell you why I find this interesting. We saw the Rodwell-Hoskins mechanism. In a normal world, normal rotating world, you have strong diabatic heating over here and subsidence on this side. Now, if you spin the Earth in the opposite direction, Rossby waves will also be in the opposite direction. So I was expecting that subsidence will be on this side and arid climate on this side. And that is what we see. But I was not expecting monsoon to develop over here because high albedo, and also because there is no Himalayas, no physical barrier to the north. So I did not expect strong convection, strong precipitation in this region. But that is not what happened there. So we will examine what happened there and why. So I will start with transients now, not the steady state, but the transients. So this is the first 300 years of the model integration, right? Control is in star, and this is the first 300 years. What is plotted is surface albedo over Sahara. Okay, I have taken this one large region, land only, and this is albedo. It's around 0.3, almost close to 0.4, high albedo. You can see that the first year it is the same as control. Then it gradually decays over time and reaches the steady state value, which is in the dashed line. That's the steady state value eventually. This is a full Earth system model. So it has interactive vegetation. Subsequently, vegetation will grow and that will change albedo, right? But what I'm interested in is the first few years when albedo is still very high, when vegetation has not grown. So what happens to precipitation during these years? So precipitation is here in y-axis. Now this, the plot below, that is surface albedo, what we just saw. Now this is precipitation. Control had close to zero precipitation. It's an arid region, so no precipitation. This is control climatology. The very first year after the rotation has been changed, rainfall is already close to 65% of the steady state value. Steady state value is in this dashed red line. So the very first year itself, some things are happening, some processes are taking place, and these are fast processes, not the slow ones, which create this very large increase in precipitation in spite of high albedo. There is subsequently very slow growth. That slow growth is associated with growth of vegetation. So this is where the Charney feedback comes into picture. Okay. So here is now precipitation in the plot below. This is precipitation, and what is shown here is F12 over the same region. So in control we have zero precipitation and slightly negative F12. This is consistent with observation and what we have seen so far. It's an arid region subsidence and F12 should be negative. The very first year after reversal, when precipitation has already jumped to about 65%, F2I is also quite high and positive. So why does F2I change? Here is a plot of the first year after rotation is reversed. So this is the 365 days F2I is for control and retro. You can see that F2I for control only slightly becomes positive during some of the months. Most of the time it is negative. For retro, it becomes positive during the summer months and then goes back to negative. If you look at the absorbed short wave, there is almost no difference between the two simulations in the first year. But there is a big difference in OLR. And when we examine further why this OLR is changing, nearly equal contributions from cloudy sky, water vapor. The same thing which we saw in the modern climate, modern climatology between Sahara and South Asia. So a little bit of mathematics here to understand the diagnostics between green Sahara and dry arid Sahara. So this is the same equation. Now this is precipitation minus evaporation. Q here is F2A, and that's the total energy into the atmosphere, gross moist stability. So what we can do is we can write this equation. If this equation is for the control simulation, then this is for the reverse rotating world. So T minus E, the control, plus the perturbation, whatever the changes have occurred. Delta is the perturbation here. So this can be rearranged to something in this form, where we have the fractional change in T minus E, and this is contribution from QDIV and contribution from GMS. So if I take the denominator here, multiply on the other sides, then it will be change in T minus E, contribution from QDIV and contribution from GMS. So let us look at what happens in this region. This is the region I have taken, and this is the delta P minus E. After Sahara has become green minus the regular control, the control simulation. So P minus E has changed by 3 millimeters per day. The biggest contribution, almost 2/3, comes from the top of atmosphere changes in top of atmosphere fluxes. So so therefore I'm going to decompose the top of atmosphere fluxes. Most of it is OLR, very little contribution from albedo. So if I decompose this further, clear sky, cloudy sky, nearly equal contribution. So the same story that we see between Sahara and South Asia in modern climate is what's happening over here when the Earth is spinning in the opposite direction. So where does water vapor come from? So this is control. Color here represents column integrated water vapor. The arrows is vertically integrated moisture transport. So you have the low level jet carrying a lot of moisture from Indian Ocean, Arabian Sea into the monsoon region, South Asian region. Strong jet, lot of moisture over here. This is the conventional control that we are all used to seeing. Interesting things are in the retro. So you have the low level jet reversing. Now from Somalia jet, now it is Sumatra jet or Myanmar jet. So it is going from Bay of Bengal over to the Indian Peninsula and into Middle East and Sahara. So you also have one more branch from the Atlantic Ocean converging into this region, and that is what creates a very strong convergence of moisture in this region. Okay, so this is all coming from pure dynamics. Once dynamics has pushed enough moisture, radiative equilibrium is disturbed. You have radiative heating of the atmosphere, which feeds back into large-scale circulation, and you have the whole monsoon growing over here. So this is the same plot for plot of OLR clear sky, water vapor, OLR clear sky, and surface temperature. For retro in circle and plus is control. In this model, with these experiments, you can clearly see that for control over Sahara, it's a linear function of surface temperature. There is no much linearity between clear sky OLR and water vapor. But in reverse rotating world, the clear sky OLR depends entirely on column integrated water vapor. There is not much contribution from surface temperature in this model. Whether it is so in this model, this is what's happening. So now we have seen what happens to monsoon over this region. Let us look at what happens on the other side. In East Asia, we saw that there is descent and there is desertification that is occurring. So let us take a very quick, brief look at what happens on the other side. Now, this is a very interesting plot. I want to spend a couple of minutes on this in detail. So this is control. Okay, we have ascent over here in blue region, descent over the red box here, right? So what is plotted is omega 500 for all of the days of a year. So this is climatology. Okay. Now look at this region, the region of ascent, blue. Let's focus on that first. Okay. During the non-monsoon months, it is positive. Omega 500 is positive, which means there is descent. Right? Come monsoon, it becomes negative. So there is ascent. And then it gradually goes away, abrupt transition, gradual decline. We know this thing. Look at what happens over this region of descent. It is descent throughout the year. During these months, non-monsoon months, the descent is associated with the Hadley cell. During the monsoon months, the Rodwell-Hoskins mechanism ensures continuous subsidence, plus albedo and aridity ensures that there is radiative cooling and subsidence. Right? So therefore, for these all three reasons put together, during different seasons, different months, different reasons, but throughout, all in all, at the end of the day, you get subsidence throughout the year. What happens in retro is something interesting. Let's look at the region of ascent, which is now this region. I'm choosing this box. So during non-monsoon months, there is subsidence. During monsoon months, there is ascent. If you look at this region, which is now arid, I'm taking land-only grids, which is now arid. What happens is during the monsoon months, when there is ascent, only during that time you have descent over here. During other months, it is ascent. So this is a very different type of desert. And this desert is purely driven by Rodwell-Hoskins mechanism. The moment you have diabatic heating in this region, you have descent over here. During the non-monsoon months, when you don't have anything over here, any ascent, any diabatic heating, there is interaction of mid-latitude eddies with the orography, this is a region very close to the Tibetan Plateau. There is quite a lot of interaction that leads to non-monsoon months or winter month precipitation. Not heavy precipitation as monsoons, but there is some sort of precipitation which ensures that the region does not become barren. So there is some amount of precipitation during the non-monsoon months, which allows some shrubs and grassland to persist. But interesting thing is that the descent over this region is only during the monsoon months when there is ascent over here. So Rodwell-Hoskins mechanism is persisting in the reverse rotating world, and that is the only reason why we have descent or aridity in this region. So coming to the final takeaways from this, all of whatever I have shown so far, the main message is that albedo has been thought of as a limiting factor of monsoon. What we want to propose here is that instead of looking at albedo, we should look at F2A. F2A is the real variable. If F2A is negative, then you have descent. If F2A is positive, then you generally have ascent. F2A depends on albedo as well as OLR. So you have two knobs to play around with. You could change albedo and get F2A negative, which will have the same effect, or you could change OLR and have the same effect. Right? So there are two knobs, and F2A is the main variable and not albedo. Okay. Secondly, I have shown this multiple times in different ways. Even in the seasonal cycle, you need F2A positive for monsoon to exist. And also spatially, wherever monsoon exists or wherever you have strong convection and precipitation, F2A is generally positive. So F2A positive is an important condition for monsoons or precipitation in tropics to exist in general. So with this and the main message also being shown here, that monsoons and deserts can be considered as a balance between radiative heating or cooling and large-scale dynamics, I will stop and I'm open to questions.
Appreciate it. We'll have questions. Hi, Chetan. Hi, that was a great presentation.
Thank you.
So I was wondering if, considering the the time to reach the steady state in your retrograde simulations, you say that most of those changes happen within the first year.
Yes.
So I would like to see what is the kind of ocean state that happens, like whether the ocean is also able to change state so quickly in 1 year.
No, it does not. In the first year, it does not change so much. There are some small changes in the boundary currents, which leads to some shifts in the east-west SST gradients. But otherwise, broadly, there are no major changes in SST.
Okay.
Because SST has not yet equilibrated. If you consider June, July, August, that is still hardly 8 months since the boundary condition has been changed. So SSTs have not yet equilibrated. It is pretty much what it was in the control.
Yeah, in that case, it raises several questions about the coupling of the monsoon system being said as the ocean atmosphere land coupled system. So one more question is that the current modern theories with data sets relating to OLR and convection, it's kind of a positive correlation, right? Like we know that SSTs and OLR is related, and spatially it is more coherent.
Yeah.
So, but when I look at your retrograde simulations, you have more precipitation penetrating inland towards Sahara and Middle East, where you don't have like ocean as such. Anything. So I was quite curious to know what would maintain that if there is an association between OLR and SSTs. I think it's not there.
Yeah, what you're talking about, the connection between SST, OLR, and precipitation, that is a general observation over oceans. But that is not the same theory which will work over land, isn't it? So over land, we need a different type of balance, a different type of theory. And over here, you can see that there is moisture feeding into this region from Atlantic Ocean and also from the Arabian Sea, basically Indian Ocean. There is confluence of both of these into this region. And this confluence is at all times balancing the top of atmosphere radiative fluxes. So that's how I would explain why it penetrates so further.
This interesting talk.
Thank you.
Very insightful. Just one question: what are the subtropical anticyclones which you see in the typical Hoskins here?
Yeah.
Which is actually tailwind waves to the east and then happening here also.
Yeah. It's just the other way around. That's
Other way around.
yes. So basically, let me try to. I did not put a plot related to that. But I think we can see some things.
In the original thing, you have Asian monsoon gating.
So sorry, I'm also
In the original, in your original here, you have Asian monsoon gating.
Yeah.
And to the east, you have subtropical anticyclone.
Yes.
So which is actually easterly coming from
Yes.
that. So that will make a base.
Yes.
And you have to the west, you have this end.
Yes.
So are we it the same thing in your in this experiment?
If you look at this, there is a anticyclone over here, which is powering that penetration from Arabian Sea into Sahara.
One more thing, in your experiment, are you taking into consideration of the desert aerosols? Deserts are known for dust aerosols. So
here, aerosols have not been considered. So what I did was I considered aerosols. Aerosols are same as what it was in the control. So whether I tested this in the RRTM, the radiative transfer model, whether I keep aerosols or not, it does not change the results that much. The contribution of aerosols is very small to OLR compared to other factors.
One more question. The thing is, are you interested in separating out the impact of two effects, that is tubular effect and then water feedback, right? So do you think this experiment is the correct one for it, or you have whichever experiment you have done, that is the correct way to do it, or something else?
So that's a good point. I would say the strength of this experiment is that we are able to show the albedo versus other factor organically without touching anything else in the model. So we could do it in a different way by prescribing albedo. Albedo can be prescribed as a boundary condition, which will then once again we will know what is happening. But when the competition is between albedo and water vapor impact on clear sky, controlling water vapor is a little more difficult. But there are techniques. Those techniques are not physically consistent. Although useful, they are not physically consistent. I feel the strength of this experiment is that we are able to show or tease out that effect without tampering with the physics. So, of course, we can do some water vapor locking experiment or radiative locking of water vapor and then prove the same thing. But I feel that is physically inconsistent. So there are other ways to do this. This is not the only way. But this has the advantage of being physically consistent throughout, although unrealistic in the real world sense.
I have a question actually. So, do you consider all the different LPT? So, your experiment actually is very interesting, which can explain the desertification, but can it also explain the aridification map? So, there are different aridity index, right?
Yeah.
So, what about the hyper-arid regions or semi-arid regions? Because you are showing a clear indicating mechanism of water vapor. So, if you change its strength, so will you also be able to recreate the aridification map?
So aridification is occurring over here during some months only. It is not happening throughout. Now, to properly assess that, I need to look at other regions where typically we have arid regions, or in this simulation wherever other arid regions occur. Here, the aridification happens to be only during the monsoon months. So I cannot fully answer your question with this experiment, but I can only say that aridification starts with dynamics, and if you can persist if you can continue to keep the subsidence during non-monsoon months, then eventually it will lead to a barren land reflectivity will change, and there will be subsidence because of that further during the non-monsoon months.
So what about the capacitor's effect of the soil moisture? Are you also considering that?
Soil moisture is considered. This is a full Earth system model. So it is there, but its impact I have not segregated.
Very nice talk.
Thank you.
Just one question. So we know that Sahara was green about before the onset of Holocene and
Yes.
middle of Holocene. So that time India also, South Asia also received very heavy monsoon, was very intense. So how does your theory reconcile this to?
So that's a very good point. If for those who may not know, 6,000 years ago up to 10,000 years ago, Sahara was green in pale climate. So that greening of Sahara is different. It is forced. So we have a change in orbit. So insolation is changing. So I can let me go back to this equation here. So what is happening is 6,000 years ago, when Sahara was green, insolation itself was different. So I'm not going to change albedo here. I'm going to assume albedo is same as present day. Because insolation is different, S minus alpha S itself will change in such a way that the numerator becomes positive. In the modern climate, with the modern insolation, F2I is close to negative or close to 0 over Sahara. But 6,000 years ago, because of orbital configuration, keeping everything else same, changes in insolation itself is enough to explain, enough to make F2 positive. That will ensure that there is convergence, and therefore, so that can be explained with this equation, and that is a forced creation of Sahara, green Sahara. In this case, we did not force anything, only changed the rotation. Everything is the same. So that was unforced greening of Sahara. That is the difference between these two experiments.
Thank you. Chetan, I like the way you presented your analysis, your work, and all.
Thank you.
Nice slides, nice presentation. So,
Thank you.
I had a question about how you consider the different components. I know you didn't consider the gradients and all,
Yeah.
right? But you consider the local forcings.
Local forcings.
Yeah. So there, for example, for water vapor, you take the column integrated
Yes.
water vapor. But for temperature, you looked at the surface temperature.
Yes.
We generally know that the tropospheric temperature itself
that is
is
also
a
important.
key factor for the monsoon
Yes.
forcing. So why did you omit it?
Let me answer that question with a plot.
Yeah.
Maybe I should have been a little more clear about that. Here, when I'm making this plot, I'm using surface temperature. This is just a correlate scatter plot between clear sky OLR and surface temperature. When I do the RRTM calculations, here the effect of temperature is surface plus troposphere, both put together.
So this is not.
This is not surface alone.
That was not clear.
Yeah, sorry, I did not elaborate on that, but this is both put together. But when I'm showing the scatter plot, it is surface temperature only. So going back to this plot here, this is the seasonal cycle of OLR in the two different regions. Here also, it is not surface temperature, it is total surface plus troposphere.
Excellent. So one more thing, I'm just curious about it. And this connects to one of the first questions as well, how the oceans respond to these kind of retrograde simulations,
Yeah.
Maybe somebody else have already done that. Just curious, I know that you looked at the monsoon,
Yeah.
But for example, where is the warm pole?
Yeah.
Do you have El Nino-like things around it? Is it on the West Pacific?
Yes, I have a plot for that. Let me, I have to go a long way. So there is one very interesting that happens. So the first thing I will show is this guy. So what is happening here is AMOC. AMOC collapses in retro in the reverse rotating world, and in its place Pacific MOC picks up. So you must remember that this simulation has no external forcing. So global mean temperature, global mean values, everything are exactly the same.
Yeah.
Even zonal mean is same. So the meridional energy transport in these simulation remains the same. It is just that the basin shifts. Instead of AMOC doing majority of the energy transport, it is Pacific which does in its place. So this is one major difference that occurs in this simulation. Now coming to the SST, I have a plot of SST. Let me. This one. So the east-west, the worm pool, sorry, not worm pool, the boundary currents will shift. Now, instead of western boundary currents, you will have eastern boundary currents. So accordingly, SST gradient in each basins will be different. And what will happen is that the cold tongue will begin from Africa and extend all the way into the Pacific region. So let me, so this is the cold tongue here, right?
In the warm pool, you have the cold tongue over there.
Yeah, yeah.
Indo-Pacific cold tongue.
Yes, Indo-Pacific cold tongue. And the warm pool is actually over here in the Pacific region.
So I forgot to ask one more question, please. So since you have said that within 1 year of your simulation, most of the rainfall change takes place.
Yes.
So in that case, I would be curious to know what kind of transients in the atmospheric circulation brings about that precipitation change, maybe checking some periodicities or some spectra in the time series of precipitation. Did you happen to look at it? Like,
I don't know. But that's a good point. One of the things, maybe we can discuss how to do that. But I have not looked at the eddies.
Yeah, because since the role of ocean and the feedback from the soil moisture is not taken into account, as you say. So in that case, what remains is probably the atmospheric transient circulations at whatever periodicities that can bring about those changes.
Right. The theory that I use is only to diagnose the final output of the model. The model itself, I just want to clarify that the model itself takes all of those considerations. It takes into account all of those considerations. The theory that I use, the equation that I use, whether it is in that or not, that's the question. So if that is not there, we can then modify the equation to ensure it is there. So one of the things initially I showed, here I'll go back quickly. This is sufficient. So F surface is something I have ignored. But F surface is where all of the contributions from moisture fluxes from surface will be captured. In general, because this is land, its contribution is negligible. The total fluxes contribution is negligible, but individually they may be important, and that may be important for short-term precipitation, day-to-day variations in precipitation or synoptic scale variation in precipitation. That may be important. This theory, the energetics theory, works on sufficiently long time scale. It should be sufficiently long that the time derivatives are negligible. So under those assumptions, these are the things that I can do. But you are right. These are certain other considerations which will help understand what's happening at shorter time scales.
We're not looking at the high frequency, but the lower frequency intersystems.
Low frequency, then that's the seasonal cycle.
I mean the intra-seasonal low frequency.
Okay.
Overload propagation or any large scale system. That is what I was.
Okay. It may be looked into, but I don't know how much. Yeah.
Okay.
Yeah.
Yes,
Yes, there.
So this is your model.
Yeah, is southern peninsula region.
Yes.
Hi, thank you for your presentation. So I am a little bit curious about the vertical structure. Like in monsoon, you see the tropical easterly jet, and above that there is a subtropical tropical jet. So how this vertical structure is changing in your retrograde?
That's a good point. We do have equivalent of the upper TEJ. Its equivalent is present, but whether it qualifies as a TEJ, I have not investigated. But we do see the shear and
so
I will not be able to answer this right away, but it is there. I have seen, but I don't know to what extent or what is the exact structure. So you were saying something? You were saying something?
No, I'm saying that if there is baroclinicity is present in your experiment or not?
It is present because when it comes to the Indian region, you have the Himalayas. There is no Himalaya here. So there will be quite some baroclinic influence. And in fact, I think that's a good point. The region I have chosen here that avoids or tries to avoid the baroclinic influence. Let me go back here. So this is the shaded region is what I have chosen. Slightly to the north of that, all of these regions have influence of baroclinic precipitation. And I did not want to take those into consideration because I need steady state rainfall. And but that influence is there. So there are two types of rainfall here. One, the conventional ITCZ or monsoon type rainfall, and the other is the baroclinic eddies related rainfall.
Okay.
So I just have one curious ask about your experiment. So you have shown around 7,000 hours of experiment in which the MOC collapses completely.
Yeah.
And your results are pertaining to the first year.
Yes.
So how are they looking after the steady state?
So
that should answer Gokul's question about SST, right?
The impact of SST surprisingly here on Saharan monsoon is not that much. Irrespective of, so if we look at this thing, the precipitation is here below.
Yeah, precipitation I totally understand because it becomes stable after that. But I'm asking about the SST, which I would.
SSTs are changing, but its impact on monsoon. Is that what you are asking?
Yes, because that's the first question from where we started.
Yeah.
So our analysis is entirely based on the year one.
Yeah.
And wherein after it reaches the steady state or not the 7,000 years ago, later where the MOC is completely down. So the SSTs are going to completely change. So the effect on the day one which we are seeing is because of whatever you are speaking. But where is the SST standing?
So this is the final steady state value. So this plot is the final steady state.
Okay. This is the final state.
This is the final steady state, and even the first year looks
similar to what you have.
there is very minimal difference here.
Thank you. If there are no more questions, let's thank Chetan again for his insightful.
What you got? Yeah. Good number of